the silver team on the step response modeling. Team members are Jonathan Briere, Jordan Buger, and myself. An outline of the presentation. I'll give you a brief background of this.
You got to push number 3 over there.
What team are you? Silver team. We have the level flow system. I'll give you a brief background of the system, show you the steady state operating curve of where we ran the parameters, and the step response, and then we'll move into the modeling. We'll give you a brief theory, results, and conclusions. Background here is the block diagram for our system. You have the manipulated variable is the motor input of the pump that will fill the level control system, and the output is the level in the fill tank. Here's a brief schematic that was done by spectacular machines that we have in our teams, showing your pump, which is your manipulated variable, a reservoir tank that provides a flow to the storage tank, and this is what we're actually leveling. This is the CFT. There's a pressure sensor, which is directly correlated to the height of the fluid. Our steady state operating curve that was presented. We ran the experiments from a range of 70 to 100% of motor input, which is on the x-axis, and the tank level ranged from just under 10 centimeters to 23 centimeters. The step response on the way up from 90 to 100 was one of the better tests that we ran. You can see the gain of the system, delta C over delta M, is around 0.88 centimeters per percent increase. The dead time was around 5 seconds with a time constant of a minute. So it was slow to respond. As you can see, if you look at the range is, I had to compress it, it ranges from 50 seconds at the start to well over 400 seconds at the end of the test. So around 7 minutes. And on the way down, it was even longer. If you look from 0 to 450, we had a dead time of 5 seconds, similar to the way up. The time constant increased, and the gain was 5.5 or 0.55 centimeters per percent. Our average gain across our steady state operating curve, as you can see, from 70 to 80, 80 to 90, 90 to 100, all are similar. They tend to stay around 88 millimeters per percent, except for 2 outliers, which is 70 to 80 on the way down and 80 to 90 on the way up. We experienced a lot of variable reaction to input, which was shown in a lot of the tests that we took. Sometimes the tank wouldn't even fill up at operating range, sometimes it would. But this is the average we got from the data that we deemed acceptable. The dead time, as you can see, increased as the input increased, which was opposite from what you would expect, as it took longer for the pump to respond as you increase 70 to 80, 80 to 90, 100, and follow the same trend. It was just backwards from what we expected. You expected as you increase the motor input that it would actually fill up quicker. It just took longer to respond is what we found. As you can see on the way up and down, follow the same trend for all 3 input ranges. Our average time constant was similar to the gain. All of them hung around 50 to 60 seconds, as you can see, except for 2 major outliers. On the way down, when we ran at 90 to 100%, it was well over 2 minutes. Was the time constant to get to 63.2% delta C, and our 70 to 80 down only took 30 seconds to reach. So it was steady state in theory, but in practice it fluctuated some, as you can see from these graphs. Now, moving into the modeling theory, you can see that CFT can be modeled using Excel, using this formula, A times U times T minus the dead time, start time, your gain, and then 1 minus your function. The parameters were the dead time, the step, the gain, the starting time for the model, your time constant, your input baseline and output baseline, which you'll see in the following graphs. For the same step that you saw earlier from 90 to 100 up, you can see the model input and model output are in the light blue and green respectively, and the experimental output and experimental input, dark blue and dark red. They line up almost almost exactly. The only difference is the shape of the step response curve you can see in the green. But our parameters that we used, we didn't even have to move around very often. We used the exact same parameters that you found earlier in your step response. The dead time remained 5 seconds. Your delta M was still 10. Delta C over delta M, so your gain was the same that we used in this function for the model. And it was the same for the way down. We used the same parameters. Didn't have to manipulate it very much. We inputted it, and this is the line that came out. So to conclude, our model equation fits nicely the experimental data without much manipulation, give or take. That means either we did a fantastic job of obtaining the data and fitting it, and that's what we're going to go with. So thank you.